This is our final lesson in Unit 14 on nuclear chemistry, and it's also our final lesson of chemistry. So we have done it, you guys. This is a great way to finish off the chemistry school year because this is a real fun way to kind of tie in what we've learned about nuclear chemistry so far and see how it actually applies and has affected us in the real world. Okay, so our lesson today is on half-life, fission and fusion, and nuclear applications. So half-life, I love half-life because the term kind of tells you what the definition might be. So the half-life is the amount of time it takes for half of a radioisotope to decay. So we know radioactive decay does occur when isotopes are unstable, okay? The half-life is a time, a number in either seconds or years or hours or whatever, but a half-life is the time it takes for half of something to go away, okay? So if I have passed one half-life, I now would expect my percentage of what I started with to now be at 50%, okay? Undergoing two half-lives, that means I would now go to 25%. Three half-lives would be 12.5%, et cetera, et cetera. So if I just look at the number of half-lives that have elapsed for a radioactive isotope, it's me taking whatever that total amount is dividing it or halving it every single time. So look at the shape of this graph right here. I have this wild decay to where you get towards that kind of baseline of 0% pretty quickly with only a relatively small amount of half-lives. Okay, so what we're looking at here, if I have the total original starting amount of my radioactive sample, this is percentage here, after one half-life, we have half of it decaying. And after a second half-life, we have half of that half decaying. And after a third half-life, we have half of that half decaying. So very quickly, we get to complete decay. So let me be clear that when I say decay, I do not mean absolutely disappear. It just will turn into something else, a more stable isotope of what it was before, okay? Through the processes of alpha, beta, gamma, et cetera, that we learned last time. So here's kind of like a more better way to visualize this, okay? So it says polonium-216 turns into lead-212 as a result of undergoing alpha decay. The half-life of polonium-216 is 0.16 seconds, okay? Here's what a sample of polonium-216 would look like after three half-lives, okay? So a half-life means for polonium-216, it's 0.16 seconds. So after 0.16 seconds, one half of that polonium has now turned into the blue thing, which is now, I'm told, lead-212. Well, a second half-life means another 1.6 seconds, half of this remaining red thing now has decayed into blue. And then after another half-life or another 0.16 seconds, half of this remaining has decayed as well, okay? So this is three half-lives. I can see that three half-lives, if I add 0.16 three times together, that would be taking an overall amount of time of 0.48 seconds. So like half a second, you guys, that's real quick, right? So polonium is going through a half-life crisis, maybe. All right, so here's another way to look at it. So a radioactive isotope has a half-life that is constant. And here's the trick. It depends on what that isotope is. But knowing the isotope of knowing the half-life of a radioactive isotope can allow us to predict things. Like we can predict the amount of measured radioactive material that might be left after a certain period of time and use that information to maybe learn something else. Okay, so looking at this, I can see my original starting amount of my sample of 100% of it is there. After one half-life, half of it is turned into red, et cetera, et cetera, et cetera. Okay, so uranium is a highly radioactive substance, okay? So over time, it will change in some way to decay into, in this version, lead. And we can see that in rocks. So like I said, half-lives are different and dependent on what that isotope is. I can have a half-life of, like we saw, the polonium of like a half of a second or even less. I can also have a half-life be a real big number, okay? So here's some examples of some common isotopes that are useful for us in some way, but you can tell that their half-lives are very, very different depending on what they are. Technetium-99 is a radioactive isotope that we use in medical diagnostic scans. It has a half-life of 6 hours, which makes it useful, meaning it's not going to hang around in our body for very long. Iodine-131 is also important in medicine because we use it to study thyroid metabolism, also finding leaks in water pipes. His half-life is 8.14 days, okay? Cobalt is also used in medicine for radiation therapy for tumors as a targeted specific thing. Half-life of 5-ish years. Carbon-14 is for dating, okay? We can measure the age of something that has ever used photosynthesis by measuring the rate of decay of carbon-14, who has a half-life of 5,760 years. And then we got some uranium here, okay? Uranium-235 is the most common type for nuclear fuel, which we'll be talking about here in a second, with a half-life of 713 million years. And uranium-238 is helped used to determine the ages of the Earth, okay, with a half-life of 4.5 billion years. So the large variation in half-life, but it all depends on what your isotope is, okay? So radioactive dating, that's where we use carbon-14 typically. It's where we use the half-life measurements of these elements, these radioactive elements, which are used to determine the age of certain geological objects or fossils, okay? So by knowing, and I have some variation here on some of the isotopes that I can use to try to do radioactive dating, okay? But if I'm looking at like carbon-14, I look at the rate of decay of carbon-14 over time, and that is an indicator of fossils, of how long or how old they may be. You look sensational this evening. This is radioactive dating. Okay, so this is all, half-life is super important for us, right? Is there an equation that you can use to calculate different things about half-life? Yes, here it is. That looks real fun, and you guys, for this first year chemistry course, there is no reason for us to ever need to use that equation. We can be smart in our brains and understanding what the concept of half-life is and what that means. I think we can use some simple math strategies to kind of execute the level of half-life problems that I'm going to require of you. So here's our practice problem. It says the half-life of aluminum-28 is 2.31 minutes. How much of a 304 gram sample of aluminum-28 would remain after 3 half-lives? Y'all are like, okay, well, how am I supposed to do this? I'm asking how much of that original 304 grams would still hang around after it has gone 1, 2, 3 half-lives, okay? A half-life is the time it takes for that number to be cut in half, okay? So I can say after 1 half-life, that 304 would go down to, now 152 grams. Okay, I've taken that number and dividing it by 2 or halving it, okay? Well, that's 1 half-life. I want it to undergo 3 half-lives. Great, let's do it a couple more times, okay? After the second half-life, having that 152, I now have 76 grams remaining. And then after the third half-life, halving that 76 again, I have 38 grams of the aluminum-28 remaining. See, this is good. We can just do the dividing by 2 3 times to represent what is left over after 3 half-lives. I could also extend this and say if aluminum-28 decays into silicon-28 by the process of this, okay, how much of the silicon-28 would be created after 3 half-lives? Well, this is going to turn into silicon-28 in some amount. We knew after 3 half-lives out of the original starting 304, we now only have 38 grams left. So the difference between 304 is 38, and 38 is what we have produced of silicon-28. That's what has turned into, okay? So that's 266 grams, okay? I can also say something like this, well, how much time has elapsed after 3 half-lives? You were like, okay, I don't know. Well, I told you up here in the problem that a half-life is 2.31 minutes. Well, after 3 half-lives, how much time would that be? I just take 2.31 minutes and I multiply it by 3. So this entire process would have occurred in 6.93 minutes. So this is the level of rigor that we're going to expect for you to do of half-life problems in a first-year chemistry course, which is not too terrible. Now let's get into the good stuff today. Okay, we're going to talk about 2 processes that are kind of opposites of each other, but equally exciting and explosive. So we're going to talk about nuclear fission and nuclear fusion, okay? Nuclear fission, you can see by my picture here, it maybe is going to lead into what the definition of fission actually is. Oh, hoo boy, I'm hungry. Me too. What's in the fridge? Just a couple atoms. Want to split them? Sure. Boom. Okay. So fission is the splitting of one nucleus into smaller fragments. I can accommodate or create this process to happen by neutron bombardment, which means I fire a neutron into the nucleus of an unstable atom, making it even more stable, breaking apart that strong nuclear force and splitting the atoms into 2 or more substances, okay? That breaking of that super strong nuclear binding energy between my protons and neutrons inside of that nucleus results in an enormous release of energy. Now, here's the trick. This is the most common fission reaction, okay, of uranium-235. I break apart into 2 smaller atoms, and look what else I have produced. 3 more neutrons. And, well, a neutron is needed to start a fission reaction at ground one, right? But if I'm producing 3 more neutrons, you can kind of see where I'm going here, and that they could maybe hit some other unstable uranium-235 atoms. And yes, that is exactly what happens, okay? Fission is known as a nuclear chain reaction because many neutrons are produced from the reaction very quickly, which can then exponentially go on to start other reactions. And if each one of these fission reactions releases a lot of energy, you can only imagine how explosive and dangerous this could be, right? Okay, so here's actually the nuclear equation showing this process where I have a neutron being fired into that uranium-235 nucleus, creating now 2 daughter nuclei of krypton-92 and barium-141, and then bingo bango, yes, there's your 3 neutrons that go on to facilitate that propagation of a chain reaction. So you're like, wow, this sounds real dangerous. Well, yes, it was real dangerous because back in World War II, we dropped 2 atomic bombs on Japan, and those were fission bombs. So the atomic bomb is an uncontrolled fission chain reaction that's allowed to propagate from a supercritical mass of uranium-235, okay? This highly concentrated fission reaction releases an enormous amount of radiation with a colossal shock wave, okay? Massive shock wave. Okay, the first atomic bomb that was dropped on Japan was known as Little Boy, okay? It was dropped on Hiroshima, August 6th, 1945. And then 3 days later, Fat Man was the second bomb that was dropped on Nagasaki 3 days later, okay? And this one was actually a plutonium-based fission reaction weapon. So this Fat Man and Little Boy bomb situation was created, or the products of a project called the Manhattan Project. So I thought we would watch a real cute video summarizing what the Manhattan Project did, how they were able to develop these 2 atomic bombs, and maybe what the differences are between these 2 atomic bombs, maybe a little bit more clear.
2023 release of Christopher Nolan's Oppenheimer. Questions have been raised if Nolan would use a real atomic bomb for filming. The film explores the Manhattan Project, which involved the development and deployment of the world's first nuclear weapons. Created during the height of World War II in 1942, the Manhattan Project was led by physicist Robert Oppenheimer, General Leslie R. Groves, and a team of talented scientists. In this video, we will discuss the details of the Manhattan Project and the 2 nuclear bombs that were dropped on Japan in 1945. The Manhattan Project began as a research initiative in Manhattan, New York. The team was tasked with creating a weapon that could put an end to the war, and they did so by developing nuclear bombs. The 2 atomic bombs, known as Little Boy and Fat Man, were the first and only nuclear weapons to ever be used against another country. The bombs were dropped on the Japanese cities of Hiroshima and Nagasaki, which ultimately forced Japan to surrender, bringing World War II to a close. The first bomb, Little Boy, was a gun-type nuclear weapon that used uranium-235 as its fissionable material. It worked by using a gun-like mechanism to propel a subcritical piece of uranium-235 into another subcritical mass to initiate the nuclear chain reaction. Little Boy was 10 feet long, weighed 9,700 pounds, and had an explosive yield of 15 kilotons. It was dropped on Hiroshima on August 6, 1945, and resulted in the deaths of 70,000 to 80,000 people, with many more injured or suffering from radiation-related illnesses for decades and generations to come. The second bomb, Fat Man, was an implosion-type nuclear weapon that used plutonium-239 as its fissionable material. In contrast to Little Boy, Fat Man relied on a set of conventional explosives surrounding a subcritical mass of plutonium-239 to cause a symmetrical implosion, compressing the plutonium to a critical mass and triggering the nuclear chain reaction. Fat Man was 10 feet 8 inches long, weighed 10,300 pounds, and had an explosive yield of 21 kilotons. It was dropped on Nagasaki on August 9, 1945, and resulted in the deaths of 40,000 to 50,000 people, with many more injured or maimed from radiation-related illnesses and injuries. The bombings of Hiroshima and Nagasaki remain the only instances of nuclear weapons being used in warfare, and the destruction caused by these bombs led to a reevaluation of the power and responsibility associated with nuclear technology.
So the really interesting thing about this is how small comparatively these bombs were to the size of a human, and how much explosive power was created from this nuclear process called fission. So this is maybe an example of how nuclear fission could maybe cause some destructive results. But there are some potential good things about nuclear fission, is that we can use them for power, okay? Nuclear reactors actually use a controlled, though, fission reaction to produce useful energy. So heat from nuclear reactors are going to be used to turn turbines in order to generate electricity for us to use in our homes. So let's see how a nuclear reactor works.
How exactly does a nuclear power plant work? A nuclear power plant works to a large extent like a conventional thermal power plant. Water is converted into steam, which drives a turbine connected to a generator. This generator converts the mechanical energy into electrical energy. The only difference is that the heat, which converts water into steam, is produced by nuclear fission and not by burning coal, natural gas or biomass. The nuclear power plants of Doel and Tihange use fissile uranium oxide. Uranium oxide is compressed into fuel pellets and packed into steel fuel rods. Multiple rods in turn form fuel elements which are immersed in water within a reactor vessel made of 20 cm thick steel. The reactor vessel is subsequently hermetically sealed. The fission of the uranium can now begin by bombarding it with neutrons. In each fission, 2 or 3 neutrons are released. They in turn cause new fissions and thus creating a chain reaction. In a nuclear reactor, it's important that this chain reaction is controlled. After each fission, only one released neutron should cause a new fission. Boric acid in the water of the reactor vessel and lowered control rods absorb the oversupply of neutrons. By lowering all the control rods at the same time, the chain reaction is stopped within 1.3 seconds. A nuclear power plant with a pressurized water reactor, such as Doel and Tihange, has 3 completely separated water circuits: a primary circuit, a secondary circuit, a tertiary circuit. In the primary circuit, the heat released during the fission of the uranium nuclei heats up the water in the reactor vessel to the temperature of 320 degrees Celsius. The pressure regulator keeps everything under high pressure, so the water does not boil or form steam, hence the name high-pressure reactor. The hot water passes via the primary circuit to a heat exchanger or steam generator. This is a cylindrical device with thousands of pipes in reverse U shape. The water runs through these pipes and gives the heat to the water of the secondary circuit, which flows alongside the exterior of the pipes. The water in the secondary circuit heats up and turns into steam. The steam from the steam generators drives one or more steam turbines. These turbines consist of a series of blades installed on a shaft. The high pressure of the steam causes the shaft to rotate very fast. This in turn drives a generator, which ultimately produces electricity, somewhat like a dynamo on a bicycle. Transformers increase the voltage of the electricity produced by the generator, allowing transportation of the electricity to the end users with as little loss as possible. To cool down, the steam coming from the turbines passes through a condenser. The cooling water from the tertiary circuit passes through the tubes of the condenser. In Doel, this cooling water comes from the Schelde, in Tihange from the Maas. The steam from the secondary circuit condenses to water and is returned to the steam generator to be heated again to steam. The warmed cooling water is brought to the cooling tower. There, it cools through contact with an ascending airflow, the natural chimney effect, as it were. The majority of this water is collected in a basin at the bottom of the cooling tower and then returned to the condenser. Almost all the water is subsequently discharged back into the Schelde or the Maas. Only a small part leaves the cooling tower as water vapor.
So there's a lot of cool transfers of energy that go on from the process that occurs in a nuclear reactor. I'm taking that fission reaction and converting it to a bunch of energy. Okay, but that's all good and fun to see the cartoons and stuff, but I really, really want to go inside of a nuclear reactor and see what it looks like in real life.
Refueling the reactor is the main objective of the outage. In the reactor core, small uranium dioxide pellets are arranged in 12-foot long tubes called fuel rods. 204 of these rods are bundled together into what is called a fuel assembly. At Indian Point 2, 193 fuel assemblies make up the reactor core, where the fission process takes place and where the heat is generated to produce steam in the steam generators. During refueling outage 2 Romeo 23, 88 of these 193 fuel assemblies are being replaced with new ones at the cost of approximately $1 million each. This new core will allow Indian Point 2 to operate for the length of its final 2-year cycle.
3 more.
Initially, all 193 fuel assemblies are offloaded from the reactor core by a movable platform called the manipulator crane. Each fuel assembly is transferred to the spent fuel pool in the fuel storage building via an underwater transfer system. Following inspections of the fuel and of the reactor vessel by underwater robotic equipment, core reload can begin.
I say next core location is Route 07. Over the bridge!
Here, refueling technicians from Entergy and Westinghouse are completing the core reload by receiving the fuel assemblies back from the fuel storage building and then placing them into the reactor using the manipulator crane. Here, the last fuel assembly, 2 Delta 38, is being removed from the transfer system and raised into the manipulator crane mast.
Actually looks pretty good.
So this seems great, and it is great in a lot of ways, because nuclear energy can produce an abundant amount of energy from an initial small amount, okay? A fission reaction is so super powerful that the amount of energy is like way outweighing how much you're originally starting with, okay? It's also cleaner than burning fossil fuels, okay? So what I mean by that is if I'm burning coal or oil or natural gas, you create harmful products or pollutants in the atmosphere, right? So it doesn't really produce the stuff that you see coming from the nuclear power plants is water vapor, steam, and other non-harmful gaseous substances, okay? Also, here's like a picture of operating commercial nuclear power reactors in the United States. It's a good kind of thing for us to see where we are getting the sources of our energy from as a result of nuclear power. But there are some cons to nuclear power because the process of fission does create some waste that is radioactive in some way. Okay, now we can confine them in barrels, but what do we do with these barrels? Because these products have a really long half-life, which means they're gonna hang around for a long time and be dangerous. So waste disposal and storage of these waste products is super tricky and expensive. There are other problems that come with nuclear power plants, like strict meeting of the environmental requirements to build a power plant, the safety costs of operating a power plant, and just the general construction cost of creating a facility like that, right? So, and the waste disposal options that we have are not great, you guys. Like, what do we do with these things? We've resorted to putting them underground in storage containing facilities, in the ocean, outer space. There's some options here, but it's very tricky just to hang on to some waste that is going to be dangerous for a long, long time. So that's fission, which is really exciting, which is the splitting of an atom into smaller pieces. Fusion is the fusing of 2 or more nuclei to form one nucleus of larger mass. Now, the nuclei that I'm fusing together are usually very small atoms like hydrogen and helium, okay? In fact, what I'm looking at here in this picture is deuterium and tritium are actually isotopes of the element hydrogen, whose atomic number 1, very, very small. Okay, so in the process of fusing these 2 hydrogen isotopes, I create helium and a neutron, and oh my gosh, here's the big key thing, it's releasing an enormous amount of energy in this fusion process. So that is amazing. But however, fusion does not require a neutron bombardment like fission did. It requires a lot of heat energy To give you an example, a fusion reaction requires sustained high temps of like 40 million degrees Kelvin, and that's in Kelvin. So we're looking at a crazy, crazy, crazy high temperature. And you're like, where can that ever be achieved? Well, y'all, this is what fuels the sun and the stars. All right, that's fusion. It's a process where 4 hydrogen nuclei combine at a very extremely high temperatures and pressures to form helium and a lot of energy. So here's technically the overall nuclear reaction equation of the fusion that occurs on the sun. It is 2 hydrogens coming into one. It is just a multi-step process to create that helium atom. Okay, so that is exciting. That is where that happens naturally, is on the sun and stars. But we have used this concept of fusion to create, obviously, a nuclear weapon. We have created hydrogen bombs, okay? Hydrogen bombs are fusion reactions. They generate more energy and even more radiation than atomic bombs. However, here's the trick here, is a fission reaction is initially needed to instigate a fusion in that bomb, okay? Because I need a specifically high temperature and pressure requirement to make fusion actually happen. All right, so hydrogen bombs only started being created after World War II. And since World War II, these are the predominant nuclear weapon type that we have been creating, okay? So H bombs, since they require these hot temperatures, are often called thermonuclear bombs, okay? And like I said, the thermonuclear bomb needs a fission reaction to get started to begin with. Now, the largest thermonuclear weapon that was ever tested, which we have not dropped any of these current thermonuclear bombs in war yet, or hopefully not ever, but we have tested them. And the largest one that was tested by the Soviet Union, and it was called Tsar Bomba in 1961. So to give you an idea of the difference in energy power between fission and fusion, I think can be looked at pretty nicely here on this graph. So here are some nuclear explosions that we have done or tested before. Tsar Bomba, the effect of that nuclear energy that was produced is ginormous, 50 megatons here. Here's some also nuclear testing. These were also hydrogen bombs, meaning fusion bombs. Now, if I zip on down here to a little bit itty bitty teeny tiny graph guy, you guys, oh, here's your fat man and little boy. These were the atomic bombs that ran through a fission reaction. So there's a giant difference between a fusion bomb and a fission required bomb. Let's look a little bit more into that.
Distinction between an atomic bomb and a hydrogen bomb lies in their fundamental design, the fuel used to create their explosions, and their destructive power. Understanding these differences is crucial to grasping the magnitude of their impact on both warfare and humanity. Destructive power. Atomic bomb versus hydrogen bomb. An atomic bomb, also known as an A-bomb, derives its explosive force from nuclear fission, the splitting of atomic nuclei. The first atomic bombs, dropped on Hiroshima and Nagasaki during World War II, utilized fission reactions of uranium-235 and plutonium-239 isotopes to release devastating amounts of energy. The explosions unleashed by these bombs leveled entire cities, instantly killing tens of thousands of people and causing long-term health effects due to radiation exposure. In contrast, a hydrogen bomb, or H-bomb, operates on the principle of nuclear fusion, the merging of atomic nuclei. This process releases significantly more energy than nuclear fission alone, resulting in explosions of unparalleled magnitude. Hydrogen bombs, also referred to as thermonuclear bombs, employ a stage design that combines a fission trigger with a fusion secondary stage. The fission explosion triggers the fusion reactions, leading to a chain reaction of unprecedented power. Fuel: uranium and plutonium versus hydrogen isotopes. The fuel used in atomic bombs consists of fissile materials such as uranium-235 or plutonium-239. These isotopes undergo nuclear fission when bombarded with neutrons, releasing large amounts of energy in the form of heat, light, and radiation. The critical mass required for a sustained chain reaction is achieved by compressing the fissile material through implosion or gun-type mechanisms, initiating the explosive yield of the bomb. Conversely, hydrogen bombs employ isotopes of hydrogen, particularly deuterium and tritium, as their primary fuel sources. These isotopes undergo nuclear fusion when subjected to extreme temperatures and pressures, mimicking the process that powers the sun and other stars. The fusion reactions release vast amounts of energy, dwarfing the destructive power of atomic bombs, by several orders of magnitude: size of the holes, impact on the Earth's surface. The difference in destructive power between atomic bombs and hydrogen bombs is also reflected in the size of the craters they would leave on the Earth's surface. While both types of bombs can cause extensive devastation, hydrogen bombs have the potential to create much larger and more profound craters due to their exponentially greater explosive yield. In comparison, the explosions caused by atomic bombs result in craters of varying sizes depending on factors such as the bomb's yield, detonation altitude, and geological characteristics of the target area. The craters left by atomic bombs are typically several hundred meters to a few kilometers in diameter, depending on the size of the bomb and the nature of the terrain. Hydrogen bombs, on the other hand, have the capacity to generate explosions measured in megatons of TNT equivalent, far surpassing the destructive power of atomic bombs, which are typically measured in kilotons. As a result, the craters produced by hydrogen bombs can extend for several kilometers in diameter, leaving behind vast expanses of devastated landscape and irreversible environmental damage. In summary, the differences between atomic bombs and hydrogen bombs are profound and far-reaching, encompassing their destructive power, the fuel used to create their explosions, and the size of the craters they would leave on the Earth's surface. While atomic bombs rely on nuclear fission of uranium or plutonium isotopes to release energy, hydrogen bombs harness the fusion of hydrogen isotopes to achieve explosions of unparalleled magnitude. The devastating impact of these weapons underscores the urgent need for international cooperation and disarmament efforts to prevent their use and proliferation.
So both fission weapons and fusion weapons produce a massive amount of energy from this nuclear process by disrupting that nuclear force. Fusion being obviously the more scary for sure of the two types. So, I mean, you're like, okay, well, great. It produces more power. Can we also make that into a useful way? Well, I mean, you're right. Fusion reactions generate a lot more energy than fission reactions. And you guys, their products are actually less harmful. They're not the wild radioactive particles that exist, or radioactive waste that exists for forever that we have a problem to deal with. Also, the fuel, meaning what I need to start a fusion reaction, hydrogen, is like abundant. It is everywhere. So naturally, fusion reactions are the way to go. I should be doing fusion power plants all over the place, right? Well, we got some problems, okay? Research is being done still to try to use fusion instead of fission for nuclear power plants, but there are several problems that make fusion reactors unsustainable, okay? We've got some super high crazy temperatures and pressures that are required to get that started, and controlling that in terms of the material requirements and the energy requirements is very, very difficult. So let's look at where we are currently with the future of fusion reaction development and seeing where those problems still are currently.
2, 1, 0.
This is the record-breaking reaction. It is more than 150 million degrees centigrade. 10 times hotter than the heart of the sun. And it happened here, the world's most powerful fusion plant, Jet Fusion, in Culham in Oxfordshire. It is, say the team here, a landmark for this technology.
These results are really significant because what we've managed to demonstrate inside Jet is that we can create a mini sun, the right kind of mini sun, hold it there for a sustained period and get really good performance levels, which is a major step forward in terms of our quest to get to fusion power plants.
Most nuclear reactors use fission. That's when big, unstable atoms like uranium are split in two, releasing lots of energy and radiation. Fusion is different. It involves forcing atoms of hydrogen together, fusing them to create helium, as well as lots of energy and just a tiny bit of short-lived radiation. Creating mini-stars inside reactors like this is one of the greatest technological challenges humanity has ever faced. Get it right, and it holds out the potential for producing almost unlimited supplies of energy pretty much forever. The key part of this reaction only lasts for 5 seconds and only generated enough power for 60 kettles, but it is an important proof of the principles of fusion. But it means there is still lots of work to do. Do you think you'll see commercial fusion in your lifetime?
Yes, I do think we will see commercial fusion.
You're confident we will?
Yes, I am confident. I want to believe in it.
So answer me this, why is it taking so long?
It is hard. It is really hard. It is very complex, but it's worth it, and we just have to do it for the future.
In a laboratory south of Montreal, Canada, scientists are busy trying to build the pathway for a new energy solution. Fuse is a startup on an incredibly tricky mission to commercialise nuclear fusion, and we've been granted exclusive access.
Right here is our assembly area.
Fusion is a process that occurs naturally inside the sun, and it's what powers it. When two atomic nuclei combine, they release energy. Here on Earth, scientists have been trying to recreate that for almost a century, but now, in the midst of trade wars and with our environment hanging in the balance, the race is on.
Unlocking fusion power is going to be technology that, will propel humanity and unlock civilization prosperity for centuries.
The promise? Virtually limitless and more or less clean energy. For the nation that cracks it, energy independence and a windfall of riches. They've built Titan, a pulsed power driver capable of producing lightning in a bottle, the equivalent of 800 strikes at once.
And this is Titan.
Whoa. Check that out.
Yeah, it's a 1 terawatt. The key innovation here is how do you trigger 238 of those bricks within less than 2 nanosecond delay or jitter between them. And that's kind of our core technology, is being able to build that triggering system.
Despite efforts here, the rollout of nuclear fusion as a practical solution could still be decades away, according to experts who cite significant scientific and engineering challenges needing to be overcome. Billions of dollars are being poured into cracking fusion globally, and competition is close by. Sam Altman-backed Helion just secured $400 million odd for its efforts in its latest funding round. Several countries around the world are also gearing up. China's reactor, dubbed the Artificial Sun, is making massive strides. And in the UK, the Atomic Energy Authority aims to open the world's first fusion power plant by 2040.
They're going through the final checklist preparations before they fire up Titan. My hands are getting sweaty. Don't know why I'm getting nervous.
3, 2, 1.
Will we solve it or not? To be determined. Are we going to make a large contribution in solving this large monumental problem? Yes, we're already doing so.
So here's a map of the sites in the world where we are currently trying to study how we can maybe harness some of this fusion energy to make fusion-generated power plants. Here is kind of a size comparison between a currently testing fusion reactor. It's the tokamak test reactor in China, but this is what the size of a fusion reactor would look like compared to what a currently used fission reactor is. And the last little cartoon, it says, hot enough for you? Oh yeah, I could sure go for some refreshing ice cold fusion right about now. Not that fusion is cold. Fusion actually produces a great deal more energy, but the products or the waste products after the fusion reaction happens are clean and safe and not radioactive and dangerous like the products from a fission reactor are. We're actually going to break this last lesson topic up into 2 videos because there's a lot to kind of just enjoy and learn and expand on and watch some extension videos for. So stay tuned for our second lesson video where we'll talk about the effects of radiation exposure and maybe some other good ways that we can use nuclear chemistry in the world around us.